beginning from today, we're going to talk about the meat, more meat than um, vegetables, I guess. The first week's vegetable, um, or juice. No juice anymore. Um, okay, now let me start. I will share my screen. Oh, before I forget, Elaine, let's do that again. Okay. All right. Thank you. So, share my screen. You see it? You all see it? Good? Okay. Okay. So the topic today is overfitting and trant-test split. So it's not just that. More, it's just keywords here. But if you're familiar with these words, these terms, you kind of what I'm going to talk about. I will explain what do they mean, and most importantly, how to do them right, how to understand the concepts, and we will do hands-ons. I will do demos. You can follow with me. I will demo mostly the trant-test split and hypothesis testing. So let me remind you, homework 1 is due by the end of this week. I think it's Saturday, but refer to the syllabus for specific deadlines and time due date. All right. The list of topics here. We talk about overfitting mostly because it is a topic that you cannot get around when you train machine learning models, and specifically the supervised learning models. You can't go around this topic. This overfitting is not only related to machine learning in computer science, but it's also relevant to statistics. So it's not only, the statisticians only are aware of this. And with overfitting, you also have underfitting, right? And both of these terms are familiar to the statisticians as well. Not so much to econometricians, but they also deal with forecasting problems. So they are aware of overfitting. They don't deal too much about that. And I'm going to talk about how to detect overfitting. We focus more on overfitting than underfitting because underfitting is much less worrisome. It's much easier to deal with and understand than overfitting. I'll talk about how to detect overfitting, but most importantly, how to deal with this. Mostly how to treat it if it happens, and how to prevent it at different levels. You can prevent it at algorithm level. You can prevent it at data level. You can prevent it after training. You can take a retrospect and diagnose the training process and to understand whether or not there is overfitting. So among these topics is the trant-test split, the testing set concept, and cross-validation. You probably have heard about it. And I'm going to talk about the details of these. And to conclude this chapter, or to conclude this module, we will talk about hypothesis testing. It's something that hypothesis testing and overfitting is not really linked together by a lot of domain experts. But to me, who works on research on theoretical problems, but data related, empirically verified theoretical problems, as well as predictive modeling. I find hypothesis testing to be really worthwhile, really beneficial here to include that as part of the routine in conducting a data science analytics projects. There is a niche that hypothesis testing can provide to have a little bit more confidence when you try to deal with already complex problems. So that's an overview. Overfitting. Now, if you have taken my other advanced programming course, I talked about overfitting. This must be very familiar to you. If you haven't, then hear me out. Overfitting is a problem mostly because these machine learning models are powerful in trying to catch whatever is the correlation, association, or the sort of the patterns in the data inside the variances. Our human eyes are not made for that. Machines' computational powers are made for that. But the problem is that machines will mistake every association as a pattern. So it may cross the line and catch up noise. Machines by itself, by the linear algebra it is not able to differentiate between what's patterns and what's noise. Patterns are what we call generalizable results, and non-generalizable results are what we call noise. The line is subtle between the two. Here, by result, I do not mean the prediction outcome of the models. I'm not saying some of the prediction outcomes, predicted labels or predicted values are pattern while others are noise. No, it's not at that level. It's more at the underlying aspect of the relationships between the variables, mostly between target and the input variables. Some of the relationships, by relationship you can understand as correlation, or you can understand it as higher level correlations between across several of the variables. That may be, that may be conditional correlation. Correlation between two variables is dependent on a third variable, and you may go beyond the third variable. Anyway, that is a higher dimensional relationship. Those are what I mean by the results. If it's strong in the data set, it could be that it is strong by nature, or it could be that it is strong by chance. If it's strong by chance, we define it as noise. It is those patterns that are not typically or commonly found or verified in another sample of the same thing. For instance, you have a sample of customers, and all the 5 customers whose name is John made large purchase amount. Does it mean that you collect another sample and the 3 Johns in that another sample will also make large amount of purchases? That is a question to ask. To what extent is the John simply because their name is John helps you predict that a future John will behave similarly as in the sample? That is a question to ask. So I hope this is intuitive. Overfitting happens because model is able to uncover and remember whatever is discovered about the associations and correlations between the variables in the data set. And we used to face a situation where data is valuable and data is scarce. We don't have a lot of data. So there is not many good ways to help us verify whatever we discover in the data, because the data were we had a lack of data in the past, so we didn't have opportunity to verify. Now we have much more data in many cases, so we do have the abundant opportunity to understand the tools to leverage the abundant data and verify and try to detect overfitting. Usually, but machines can make overfitting problems. Is there any kind of sort of higher level patterns in terms of machines? What are some of the good machines? What are some of the good machine learning models that tend to pick up more noises than pattern? What are those that are more immune to overfitting as a problem? As a sort of, let's see. Rule of thumb, right? I'm trying to search that word. Rule of thumb is simpler models tend not to be overfitting. More complex models tend to be overfitting. Simpler models tend to account for the most basic patterns, while more complex models are able to go beyond the fundamental patterns and pick up more nuanced patterns. So that's another word that we describe noise. More nuanced patterns, whatever however strong it may be in one sample, it could be because of chance, and it may not be verified in another sample. That's when we can be certain that that's noise. But we have many modeling framework. Within all those frameworks, we can go from simple model to complex model. So here, when I say simple models tend to account for more basic patterns, I'm talking about the comparisons of models within the same framework. So I don't encourage, or I discourage you to compare model frameworks. Let's say, regression model versus neural network model. I discourage you to compare regression with neural network. I encourage you to compare different levels of complexities of regression models and different levels of complexities of neural networks. As you go from more simpler regression models to more complex regression models, you can find the same pattern here, which, more complex regression models tend to pick up more noise. So let's do some thinking, discussion, talking before we delve into more technical materials. So along with the line of discussion I outlined just now, let's think about several modeling framework, and under each modeling framework, let's think about and talk about what you can think of as simpler versions of that modeling framework and more complex version of the modeling framework. Three types of modeling framework we're talking about. The first is perhaps very intuitive and by its nature, is by using sample statistics to try to estimate or try to make a prediction And this is intuitive because if I ask you to predict the president, age of the next president, how would you estimate that? You probably will take a look at the 50 presidents in the US history before this point and take an average. So that might be your simplest, but probably a good, proxy for you to make a guess. So using sample statistics has been a traditional way of making predictions, and you won't be far off. By taking the average of the past 50 presidents, it's very unlikely that you will get a statistic, mean age of like 8 years old. You can't get that because none of the youngest, maybe 40 something, President Obama is 40 something when he was elected. And of course, there were presidents who were more senior when they were elected. But either way, by taking a sample of the relevant past examples, it's a good estimate. It's a reasonable estimate. May not be the best because it ignores the contextual information. We are in 2020 and we're in 2021. The age pattern may be shifting, right? So so think about in this simple sample statistic framework, what can be a simpler model and what can be a more complex model. Or by model, it doesn't have to be sophisticated algorithm. It simply has to be a way of calculating or estimating or putting things together to make an estimate. So that's one framework. The second framework is regression. You must be very familiar with regression. You can name a few examples of different regression models. Linear regression is one, polynomial and whatnot. So the same exercise under that framework. And the third category is neural network model. There are simpler and more complex neural network models. Neural network has become a catchword nowadays. Nobody will pretend they don't know about neural network. Everybody knows about neural network, although it's doubtful everybody understand what a neural network is, not even to build it. So we can talk about the same set of questions under that framework. Let's do a breakout room discussion. You can choose any of these three, or you can hit all three if you're ambitious. Either way, and then we'll convene and talk about your results, your discussions. So for today, I'm going to stop the share for now, and I'll create Zoom breakout rooms. Let's see. And okay. Hey, let's see. Hey, Sarthak, are you okay? Are you not in the team? I'm going to assign you to a team, and
yeah. Sorry, I just came in.
Sure, yeah, that's fine. I'll assign you to a group.
Okay.
think a lot of people are actually buying the books right now. So I know I had one book delayed. So work in process.
Yeah, my second book was canceled, so I've got to go find an alternate source.
Great. And you know what to talk about?
Yeah, so the question was stating like basically like the different types of models, like a regression model, and what could be like an example of that.
You know, simpler and more complex model under the regression, under one type of modeling framework that you can think of.
So would that be like a linear regression versus a multiple regression, or?
It's a great point. Think about this. Linear regression is a generic term. It simply means that you can include either few or more linear variables or linear terms. And multiple regression means it's not a simple regression. It includes more than one predictor variables. So the two are almost the same thing, right? But think about how a regression model can be made simpler and it can be made more complex.
So I think like an example of a regression model. Last year I did a project for one of the classes. It was with restaurant data, and they had 5 or 6 different variables. And then we kind of did a linear regression model seeing what 2 variables were most correlated with higher sales in the restaurant. I guess that could be like an example. We did it in R, and we used package, and we used some linear regression modeling on that.
Okay, so that's a linear regression model. Have you played around increasing the complexity of the model or decreasing the complexity of the model?
Yeah, so you can like add more variables to it and see kind of like the different values, like a p-value and the different thing, like you do the t-test, take a little sample from there, and you kind of can add variables or subtract variables to see how each variable corresponds with how strong the correlation is basically with the sales that we were trying to figure out.
Mm-hmm. Great. Keep going. Keep going.
One of the things we did for our project last year in one of the multiple regression models was
Hello, everybody. You're discussing. Keep going.
Yeah, like we were just discussing like which one is the simpler model compared to the three main ones. Like we felt like Adeline might be a bit difficult because like it has a couple of drawbacks in regression in comparison. Like there's like training convergence, and there are more variables in Adeline, which could make it a bit complex, and regression doesn't have that many variables in comparison.
Right. So I said I encourage you to compare models within the same modeling framework. It will be hard to compare across the modeling types. The regression models and neural networks are different. They are different animals, although there are similarity within some of.
I was just wondering, what's the name of the owner? It doesn't show on the tax records. What am I supposed to put there?
So the breakout room is.
Do you want me to leave that blank? Because I left it blank for you to fill in, but.
Hey, Justin, you're not on mute.
Hey, Justin, can you mute?
I'm on zip forms, but I can.
So I guess let me. Okay.
Oh yeah. You're right about that.
Let me mute him. Yeah, great. Anyway, that's amusing. So we'll come back. Any group have any fruitful discussions and results? Did you converge, or is there a confusion? to think about how to think about this? Feel free to talk. No, not much.
So I joined the group discussion for my group pretty towards the end, but one of the things I was telling them was that last year for one of our projects we had the age variable, but there were groups in the age variable that had different assumptions or possible different assumptions. So one of the things we did in addition to running the complete data set as a regression model was split the data by the different age groups and run it again to see if the same variables are still significant or not, and if the correlation had changed. And so that was one of the ways we kind of added complexity to the regression model, was
Okay.
to.
So I hear that. That's what we call let's see, conditional correlation, or conditional. Yeah, we can say conditional correlation. It's the underlying mechanism of that is interaction between input variables. So essentially, the correlation between an input, which is age, let's see, or something else, with the target variable, the variable that you're interested in, is conditional on the value of another variable, say age. Yeah. So, the effect of wealth on purchase likelihood depends on age. So that is more conceivable to think about. Exactly. So adding interactions makes the regression model complex. That's right. So that's one way of, simply adding additional variable on itself, which we call a main effect, is another column of X. Adding more columns of X variables into the model, it increases the complexity of the model, but not exponentially. It increases on a linear kind of fashion, but so it doesn't increase the model dramatically, unless you include hundreds at a time. Then you can get overloaded. But increasing the complexity of a regression model. So we're talking about the second point on second modeling framework on the slideshow. Adding square terms or adding interactions between between input variables can quickly and exponentially increase the complexity of the models, because in a way you are assuming that the interaction and the quadratic and more higher level terms are making a sort of structured influence on the y variable, and those assumptions will quickly make the model very complex, and it requires more computational power to find a solution that is confined to the model that includes more variables and higher level terms. So that is the mentality of thinking about creating or increasing complexity for regression models. For simple model, let me share my screen. Let's go back to the slideshow. You can see it? Great. So under the first modeling framework, sample statistics using the mean or median or mode for different types of variables or for variables that are skewed, or perhaps the simplest model that you can build. We also consider it as a model because you can write equations about mean, right? As long as there's an equation for an estimator, it's a model, but it's rather a very simple model. But you may wonder how to make it more complex. Well, you can do different averaging. You can do different weighting. How to estimate the most likely age of the next president, or how to forecast it. You can take the average of all past presidents That's the simplest example I talked about. However, the age of the president may be going on a trend. You don't know what the trend is, but if you put more weight on recent presidents and put less weight on, more the presidents in the more past, then you have a more complex mechanism to using the mean or using the average, which is the weighted average of the sample of the presidents to estimate means, to hopefully capture a trend, whatever the trend is. And so this technique is the moving average or some weight decay kind of a model that puts more weight on more recent events or more recent data points, which is conceivably easy to understand that the stock market use it to forecast how the stock price will move in the next day or so. It puts more weight on the recent events and recent, I don't know what that means, 80%. So you can quickly add, by adjusting the weight mechanism, you can quickly increase the complexity of the model even more. So that's a way to think about. Why do we think about that? Simpler models are more likely to capture the trend, and the simpler model or the result of the simpler model will be less likely to go off by a large margin. By taking the mean of all the president's age, our forecast for next president's age is not going to be a joke. It's not going to be too surprising. It's going to be within a reasonable boundary. It's not going to be, the number won't be funny. We won't come up with an estimate which is 100 years. People already dead. No, it's not going to be possible. It's going to be reasonable. However, the error, you can almost be certain that it won't be accurate because it ignores many other trends or other contextual information. By increasing the model, you may be able to capture an age trend so that you can decrease the error, you can decrease the bias of the estimate and get a closer guess. However, by increasing the complexity of model, you could end up getting a very bizarre estimate because somehow the data indicate there is a trend, but that is really a noise, which pushes the model off the track. The model relies more on those nuanced trends, which will come up with an estimate that might not even hold reasonable. So that's the trade-off between simpler and complex models in getting a reasonable versus more accurate, but sometimes surprising prediction. So that's under the sample statistics framework. Regression model I talked about. Neural network model, simpler model would be the Adeline. The simple neural model we'll talk about beginning next week. That in that model, you only have one cell, one one neuron that is designed to sort of to imitate or to replicate how human neurons work. That's a single layer perceptron model or Adeline model or logistic regression model, very similar. But more complex models, deep learning, So I don't need to talk too much about that. You have heard a lot about these. Any questions so far? Good. Okay, a motivating example here. Let's make two models. Let's make a complex model that predicts very well. But then also let's make a very simple model that could make some mistakes, but will overall be a good estimate. So this problem is about predicting or classifying the label, which is a color indicated as a color of the point. We have only two colors. Let's think of these as let's see, because the numbers are quite equal. Let's think about political party affiliation, right? Sounds good. Let's think about, let's assume that the black dots are Republican, and let's assume the the gray dark dots as the Democratic. Okay, there are only two parties. So, and we have two variables to help us predict. Both x, y are predictor variables. They are not target, right? And can you imagine a simple model, the simplest model, to help you separate Democratic from Republican? And how would you imagine the model will be? You don't have to talk in terms of math or anything technical. Simply, use a simple tool, visual tool, to help you simply, separate them, which could be helpful to predict what this question mark should be. It stands for a point that we're trying to classify. We don't know the label yet. We try to get it. So what might be a simple model?
Just a
Yeah,
sorry.
I heard it. Abhinaya, right? Sahiti.
I say it's just a simple line, single line, which is separating the two different colors.
Okay, so let's see. Let me try. Hold on. Pen, red, like that. Green. Okay. Now, if it's a straight line, it looks like I can do this, but I need to somehow tilt it because the boundary here, the frontier, kind of is tilted. So let's do this. May not be good enough. I hope I had drawn, half inch to the left, but let's just assume this one might be actually not bad. So two black dots on the other side, which is the error that this model is making. This straight line, assume this is a straight line. Okay, let's make it explicit. So this straight line is perhaps the simplest model that we can define here that can do a reasonable job. Few black dots on the other side, the wrong side, and 1, 2, 3, 4, 5, 6, 7 Democrats on the Republican side. So 9 errors. So we made 9 errors. Observe the fact that this line would probably could probably make a wrong guess for the question mark. The question mark could be a Democratic, which is a light gray dot. It could be because of the fact that several of the Democratic people cross the line in this region of X and Y. So that's conceivable. But it also could be likely that this point is just another black because there are plenty of blacks here. So this model can conceivably make an error with a reasonable probability, although it's more likely to make a good guess. Still, another observation is that however you move this line, if you keep it straight, it can't be perfect. It will never be perfect. You will always make some mistake. However you tilt it, you move it a little bit here, you can make sure these 3 gray points are in the right territory, but again, more black dots will cross the boundary. You can never get rid of this one. Even if you hate it, you won't get rid of that. It's going to be a mistake. So that's what simple models do. Simpler models are able to separate the big picture. The vast majority of the points are correctly classified, but you'll always make some mistakes, right? That's a simpler model. Now imagine how you can make a very complex model to try to eliminate those errors. Let's use blue. How can you do that? You probably will make a curvy line. So I have already have it in one of the slides. So probably you can think of something like that. And I'm going to draw the simple line in a minute. So this line is a complex model as compared to the straight line. A straight line needs only one variable. Right? A straight line needs only one variable or two. If it's a tilted line, it needs two variables. This curve at least will need 10 and more likely higher dimensional variables to describe this line in math term. We'll skip the math term, but you can imagine, the intuitive difference between a straight line and a curvy line is because of the higher, quadratic terms and higher dimensional terms and interactions between the two variables. It's the conditional relationship between x and y that is making a turn. So this model, let's observe how it does. It makes everything right as far as we can see on the points. All the Republican points are on the left side. All the Democratic points are on the right side. And now let's observe this question mark. By this complex model, it's going to predict as a Democratic. But, without considering this line on the overall picture, although this point is generally in a sort of like a mixed territory, it's still closer to the majority of the black points. So it's higher. It's more likely to be a black dot, a Republican point than a Democratic point. But this very complex line could make a bad guess on the question mark. So that is something you need to realize for more complex models. Because of those nuanced patterns picked up from the training data, it may make a mistake even on a very intuitive case. So that's the difference. Let me remove some of these lines here. Okay. And let's contrast this complex model with the simpler model. This is the model that we just draw in the previous slide. So, that's the difference between the two. And there's no absolute bad and good. It's always pros and cons. It's the tension between simplicity and generalizability. Make sense? Any questions? All right, keep going. This is just the slides. Okay, so this is what we call a fitting curve, or it's also called a sometimes overfitting curve or underfitting curve, also called validation curve, because there are validation sets. I'll talk about how validation set is different from test set and whether or not this is trant-test split or not. It's not actually, but I'll talk about more when I talk about trant-test split. There are two versions of the fitting curve. Sometimes we plot the model accuracy on the y-axis, but here it's plotting the error, which is the cost. error is a cause, is a penalty of the model. It's something that the model tried to reduce. The other version is in the next slides. It's using the accuracy or score, model score, as the y-axis. In both versions of the fitting curve or the validation curve, you will observe something that are similar. The x-axis is always going to denote the complexity of the model. As you go to the right, from left to right, on the x-axis, the model increases complexity. So you can think about adding more variables, or particularly adding more quadratic and interaction terms between the variables that makes the model more complex, and go to the right. For neural networks, it's adding more units and adding more layers, or let's see. Yeah, that's basically it. So in both versions, you'll always see two lines. The two lines will first move in the same direction, very typically. But after a while, one line is going to reverse curve, and it's kind of making a concave or convex curve. So it's more like a reverse course curve. But the other curve is going to keep going in the same direction, despite flattening the curve or not. Typically, it will flatten because there is a limit in terms of error. Lower bound of the error is zero error, but higher bound of the performance is 100% accurate. You can't go beyond that. So the curve is most likely going to flat as the model becomes super complex. Right. So there will be two lines. The line that will reverse a course is very likely to be the validation set quantity, either the cost or the performance. The line that keeps going without changing course is the training set performance, or the error. Because error is something to reduce for the model, the overall trend of the training set will be decreasing errors. But validation set will initially have decreasing errors, but reverse course, and to have worse errors in the long term. Then we will divide the region of the complexity for the model to be two regions. Initially, it's the underfitting region, where the model underperforms compared to the standard or expectation. Once past that threshold point of complexity, model tend to be overfitting and perform only well on the training set, but excessively well on the training set, which is unreasonable to be believable on the unseen data. Now, critical to this graph is how to find the optimal model. Using the fitting curve or validation curve, you can find the optimal model by focusing on the validation set. As long as you can confirm the divergent trend and the overall pattern is consistent with a fitting curve by using both lines, the training set line becomes almost useless. The validation set is going to help you find the optimal model. The dip point on the cost fitting curve indicates the threshold of complexity where the highest model performance can be found. It doesn't matter if the two lines cross. Sometimes they don't even cross. But whether or not they cross, the best model is going to be the model complexity that makes the lowest level of error on validation set, or using the performance is the highest level of model performance on the validation set. So I hope that's clear. I kind of talked a lot about this graph, but every sentence I said is kind of relevant and important. And here is the other version of the fitting curve, or validation curve. Here the two lines don't even cross, but that's normal. That's normal. The best model is found by looking only at the validation set line. This time it's the model performance. It's the model score typically is accuracy, or maybe it's the AUC, ROC quantity. It's the point of model complexity that makes the highest level of validation set performance. So that's where the best model is found, by using this curve. All right, any questions? Any questions before I move on? Good. Yeah, so, some of you have already seen these graphs, right? So once you understand why overfitting occurs, then these are very nice tools to help you diagnose. Okay, let me get some feedback here. How do you feel about the, given that you have read the book and you have reviewed the slides, and you may have taken other courses as well that talk about overfitting. How do you feel about overfitting? Is that something that you have a good grasp about? You think you can, you can explain or summarize what overfitting is? What is the underlying cause of overfitting? If you are confident about that, then we don't even have to go more. It doesn't mean we don't have to go deeper, but we don't have to spend more time on this. If we can go over this, then we can move on to the next topic. So, what do you think? Yeah. Can anybody talk?
I think easy for me is overfitting is overstudy.
Yeah, it's a good analogy. Or overthinking. Something like that. Overthinking happens when when the thought is unrealistic, or when the thought is unverifiable. In real life, terminology or language, but really overfitting is something that with the models that we're going to learn, it's going to be very easy. The tricky part is that you never know. With a new data set, the trickiest part of dealing with a new problem using machine learning is that you do not know where the best performance the model could be. Without having a good feeling about how well could a potential model be, without that target level, without knowledge about that target level or desirable level of model performance, it becomes harder to think about overfitting. Sometimes when we see a curve, it may indicate overfitting, but it may not. So that's when we will spend more time on the specific examples. Talking about them without the context is not very useful. So we can move on. Great. Right. I have put these two videos on the links and embedded videos on YouTube. You can find them under I created a new page. It's somewhat below on the lower part of that list on the navigation pane on Blackboard course. It's on the page, other useful videos on YouTube. And later, I've already found a good video about neural networks. It's not something that it's not something that you need to watch. By going through this course, you understand everything behind it, so you can even make that video. But I thought that once you have learned everything and done homework, and then you review the video again, you may be able to, find something that, may kind of slip your mind or slip your attention and can help you have a good overview throughout the underlying mechanism of neural network. But later I'll put that video onto it. Dealing with overfitting, two things are typically mentioned. One is the trant-test split, right? And the other is cross-validation. Let's see. So trant-test split is to split the full sample, all the sample that you have, that you could possibly have about that you can analyze the problem. Let's see, it's 7 o'clock. Let me put a 30-minute alarm. And the reason of doing that is that you're trying to create an environment which is not real, but you're trying to create an environment where there are certain part of the data that you can't get to, you can't obtain for training. So that will limit your model training to only the training set. And after training the model using the training set, you can use the rest of it, which is the test set, to test out the model, which will be an unbiased mechanism to test whether the model has overfitted or not. If the model has overfitted, and if the overfitting is so severe that it has picked up weird nuances in the training set, then you won't be surprised to find a much lower test set performance. So that gives you a very good tool, an unbiased tool to alarm you before you go ahead and put the model in implementation and make mistakes in real life. So that's a good mechanism. Model is trained only by using the training set. The test set the test set is preserved. It's rarely used. If you use a test set every time you train a model, the test set has lost its purpose. The test set has been exploited too much to the point that you have already extracted understanding about the test set. You're training a model in anticipation to also do well in the test set. Then certain techniques that you put into the training of the model may be, deviating the purpose of the machine learning training. You're trying to take shortcuts just to beat the test set. Then that's not the purpose. So in Python, we perform the trant-test split by using the scikit-learn tool to do trant-test split. And it's something like this, we have data set, which is 2D, has rows and columns, right? Columns are the variables. The trant-test split simply by using some random mechanism, random number generator. It generates the row index, and based on a ratio of test ratio, or percentage of the data point that you want to allocate into the train or test set. Let's say 0.3 is the test size, then it allocates 30% of the data point into the test set and put the 70% of the data point to the train set. So the random generator will generate a starting point, and by 70-30 chance split, it will allocate this example to train, and this is test, and it will randomly go to a second point, and by the chance, it may allocate it to test set, and then it will go ahead and randomly jump across the table, the rows, without taking the same record again. Once a record is taken, there's no chance that it can be taken again. So the program will go on, and by the end, you have 70% in the train and 30% in the test set. So this is the random process. And what is the rationale by going with a random process? Because you do not need, you want to make sure you have no idea which point could end up in the train or test set. It should be a totally random process. Now, the idea is that the less information you have, the less information about the specific points you have about the test set, the better off you are in terms of using the training set. But another benefits of using random allocation or random split is that you can make sure that the two sets will be similar to each other, so that there won't be anything bizarre. Hopefully, there won't be anything bizarre in either the training set or the test set that could mislead the model. So that's another purpose of that random split. So how can you ascertain that they are similar? How can you ascertain that the train and test set have structural similarity? That is the hard point. You never know. You can take a look at the basic statistics. Let's say there is an age variable, and then you have the train and test set. The average, hold on. The average of sample mean of age is, let's see, 45 in the train set. In the test set, you have the mean age of 44.3. So they're clearly not exactly the same. And most likely it's going to be like that because they are random samples, right? There are random variances across the two samples. How can you be sure if they are similar or not? If they are dissimilar, if the two samples fundamentally are different in terms of the age, then you have a problem. Model trained on a training set, which is able to recognize the pattern of age, which is unique to training set, will not be. So it uses the training set to learn the pattern about age, and then try to implement on the test sets. It's going to fail if the underlying structure about age is different in the test set. So how can you ascertain that? The tool that I think is worthwhile to use is the hypothesis testing. That's why I put it in here, and we will talk about that. In every project, in every homework, once we introduce train test split, we will implement hypothesis testing to make sure train test splitted data sets are structurally similar on key variables. Any questions? Good. Let's go ahead and see how to do it in further slides. So train test split is going to help you detect overfitting. But if there's a mechanism to help you prevent in the first place, that's good. That's equally good. And you have two tools. One is for you to avoid overfitting. The other is to help you catch overfitting if the avoidance mechanism fail. Regularization mechanism is the mechanism to prevent the model from learning those coefficients that lead to an overfitting model. To be brief here, regularization, once we introduce the loss, if you understand what the loss is the objective function that the model tried to minimize in learning the optimal parameters, and the objective is to make less mistakes for the model. So loss is a proximity, sort of the proxy for how many mistakes the model makes. If we can train the model in a way to reduce the loss, we can improve model performance. However, simply reducing those losses that is purely associated with accuracy will lead to an overfitting model, because a model can ultimately be trained almost to have a zero loss if the model is super complex, right? And that's a point where you're almost certain that the model is overfitting. So then the solution is to modify the loss, to modify it to avoid, to balance out the learning of the model, to also consider other factors, not only to consider purely the part of the loss that are related to prediction, right? So it adds a term to the loss. Then the question is, this is the formula, and I'll talk more about it when we talk about the add-a-line model, a more logistic regression model. We'll understand what it means and how to implement that in a code. But to talk about briefly, let's say we have a regression model, or a neural network model, or a logistic regression model, any model that you can imagine that it has a vector of coefficients. The number of coefficient is m. There are m variables here, so there are m coefficients from 1 to m, and there are from 1 to m input variables also. So those coefficients correspond to the input variables. Input x, right? So this additional term, which is called L2 regularization, is trying to calculate the sum. This is sum, but it takes the square. It takes the square of every coefficient. You know, we have m coefficient here. We take the square of every coefficient and add those square terms together. Right, so you can imagine, which is x1 squared, where 1 means the variable count. It doesn't mean observation. x1 squared, x2 squared, all the way to xm squared. We take the square root of each x and sum them over. In the end, we will sum this all over the sample. And then we multiply that by a fixed term. This is the fixed number. Lambda is a coefficient you decide, and it sticks to that. So it doesn't affect, you know, how this function is going to move. So by adding this term to loss, it balances out the incentive for the model to reduce error to 0. Adding this term will make it impossible for the model to reduce error to 0. And here is why. You know, loss is something to reduce. The model will also try to reduce this part. Can you imagine the condition where this part will be minimized? What is a condition where this entire part will be minimized? And what is that minimum? If you know the answer, just, you know, go ahead and talk. You know, just something to think about why regularization will work.
Taking in the minimum number of input variables?
Let's see. So okay, no. Sorry, I've made a mistake here. I shouldn't have put the input variable here. It should be the coefficient for those input variables. Apologize. So these are the coefficient, and W is the coefficient, and we typically use beta to refer to regression coefficient. So these are beta 1 squared, beta 2 squared, all the way to beta m squared. These are not input variable, but these are associated with those input variables. You know, so what is the condition where this giant part is going to be minimized, and what is that minimum?
The smaller the regularization parameter.
Yeah, the smaller in terms of absolute value, and the smallest absolute value is 0, right?
Yeah.
So when all the beta becomes 0, all the beta go from 1 to m. All the beta becomes 0. This part is going to be minimized, and this part will disappear, will become 0. However, think about a model where all the coefficients is 0. Will it make a good model?
No.
Not likely. It's going to make a very simple model. It's going to implement the mean value typically for regression, right? When you have the regression terms all have 0, then all the variables will not make an influence. The end of your predicted y will simply be the sort of the mu, the average of whatever the quantity that you are trying to estimate. You know, president's age, it will be taking the mean of the past presidents, and not any other single variable is going to make an impact because the betas are all 0. So that model will not be a good model. Yes. But, you know, model training will not simply minimize this part. Will also minimize the other part, which is the law, which is the normal loss. So these two go against each other. Will create some kind of a balance. The model will be between a very simple model and a very complex model to strike the balance between overfitting and accuracy. I hope that's understandable, and you know, and let me know if you have any questions. Then you may have a question. You know, where is the balance, right? Could the overfitting problem is still too big to balance out, or could it be that the regularization is too strong? It takes over and make the model underfitting. It could be possible, and all the key is relying on this lambda part. You can adjust the sign, the sides of the lambda to adjust, you know, the power of regularization to avoid a model that's too simple, or to avoid a model that's too overfitting. And we'll talk about, this is more of an empirical question. There is no golden lambda. Lambda, the best lambda is different for every problem that you implement the model. So it's more of a, you know, try and error process. Good. So we'll skip the breakout room, and that's mostly the conceptual part for regularization. We'll talk more about implementations in two weeks, I think. Good. Any questions?
Professor,
Yeah.
I have a question. What does the left side of the equation mean?
Okay, so the right side is the sort of the breakdown of the left side. So this is taking the norm of the, so because W is more of a matrix term, it's a vector. It's taking the norm, and it's taking the squared, and it's taking the inner product of two vectors. So you would multiply the corresponding element of the two vector and then take a sum. So that's exactly what the right part is trying to get at. It's explaining what the left part is doing, right? So it's taking the sort of a Jacobian inner product of the vector and multiply by a fixed term. Good?
Got it. Thank you.
We'll talk more about Python implementation. That's the most critical part. Great. So trant-test, you understand the rationale for trant-test split. And let's talk about hypothesis testing. So a few words about the trant-test split and cross-validation. And this is something that may cause confusion. Trant-test split and cross-validation. They are used in different stages of model training. Trant-test split creates the test set. So the mentality about test set is you want to learn as little as possible about the test set. So you can't do too much understanding about the test set. You want to do minimal of test set and minimal preparation and understanding about the test set. But cross-val, you want to make sure that these the different perturbations, the different sort of the cross-val sets, cross-validation sets, the different folds, typically say 10-fold cross-val, then the 10 subsets of the cross-validation. We want them to be as similar, structurally similar to each other as possible. We hope there is no too much surprises other than the random differences between them two. Though here, test set could give us some surprises, and that is a good testing environment to really test out how the model did. So talking about the process of predictive model lifecycle, a predictive model training lifecycle. Once you get the data, you do some preliminary understand about the data, and some cleaning of labels, surface level cleaning. Once you do that, you go ahead and split the train and set without doing anything else. But follow that with hypothesis testing to make sure that they are structurally still similar. There are not too much surprises. There could be some differences, but not too overwhelming. And then you go ahead and train. Train and eval. This is difficult. Evaluate the model. But during the evaluation, during the training process, you can incorporate cross-validation. So cross-validation, both the train and validate, our validation sets are within the same train set. They are split from the train set, in the first place. Test set is entirely different. It's cast aside at very early stage in the life cycle. You go through training and use validation to test the model using multiple folds, and altogether you can have a reliable estimate of how well the model did on randomly created unseen data set. Right. For cross-validation, there are also videos on YouTube you can watch. Those are quite intuitive. It's very easy to implement in Python, so I'm not going to spend time on that. I'll spend more time on this part because that's more critical here. So that's where the two are different. The concept is quite similar. The rationale between them is to reserve a part of the data to test the model. That's the similarity, but the difference is where they are used in the life cycle of the project. If they are used well in each places, you can have at least a very trustable model, based on the results. That can be guaranteed. It may not be the best model, but it can be trustable. So cross-val. Let's do some demo. Have you downloaded the Jupyter Notebook? Let's okay. Need to go to the other screen. Oh no, it's here. Right. Okay. So if you have downloaded the Jupyter Notebook, you can run these. I have uploaded a new Jupyter Notebook, which is the same, but I overwrite the Jupyter Notebook. The difference is these two lines. The original version before today, it didn't have these two lines, so the second line may not run. It may give you an error. That's because the two libraries are, the one library is not imported. That's why. But if you downloaded the new Jupyter Notebook, or if you add these two lines, it will work. So we need to import the packages and the data set before I do the split. The data set is default one. It's the same data set I talked about last time. It's about credit card customer default. This is a subsample of that data set, which is easier to learn and demo. So here is a trant-test split. There are several ways to do trant-test split. Here I'm using one way, and difference is that here I'm given the trant-test split only one data set. It's a data set that includes X and Y variables. So I'm only taking the numeric variables here, but the target variable, which is target, the name is target, the variable type is binary. It's a numeric binary. It's a flag variable, 0 and 1. So it's a numeric type. Along with the other, a long list of other numeric type input variables, this part will select those columns and feed into the trant-test split function as one data set, and the other are arguments. So if I only provide one data set, it's going to split that into two sets, a train and a test set, according to the ratio. But ultimately, in the next homework, you will learn a different way. You'll provide two data sets. You'll first split Y and X first before doing the split, and then you'll provide the X and Y together, and it will return 4 sets. You can see the difference when you look at the demo codes or when you look at the videos. The difference is the number of data sets that you provide. You can provide an infinite number of data for split, as long as they have the same first dimension, right? As long as they have the same rows for the X variable and same elements for the Y variable. They have to match, otherwise it will give you an error because the indexes don't match. If you provide multiple data sets, it's going to split the first data set into 2, train and test, and it will split the second into train and test. So always first sorted by the source data set, and second sorted by train and test, right? Make sense? Test size 0.3 is the ratio of the data points to be placed into the test set. You can provide a number, an integer number, which will put that number of cases into the test set, or you can provide a ratio. Typically, a ratio makes more sense. It's quick. It's more easier. Shuffle makes sure that the random selection takes place after the entire sample is first shuffled, and the shuffle mechanism and the random selection mechanism is governed by the random state. So by using the same random state here, I'm using 10, and numpy random seed at 3. Make sure the two numbers are the same. You can get the exact same result here. So that is splitted. We can quickly get the dimension for the two sets and do train the shape and test the shape. Because it's 7 to 3 split, you have 7,000 in the train and 700 in the train and 300 in the test. Both sets have the same number of columns. Yeah, make sense? So that part is done. Random split is done. Any questions? Good. So next, you want to make sure structural similarity. That's why hypothesis testing is useful. There are 2 relevant testing types that we'll introduce here that is typically sufficient to deal with machine learning projects in business. one is the point estimation, the kind of hypothesis testing that you're more familiar with, t-test. T-test, you probably are more familiar with one sample t-test, which is to test the sample statistic, whether or not that is equal to a quantity that you believe is the population quantity. Sort of saying, I don't know, entrepreneurs. What is the typical age for successful entrepreneurs? You may have a knowledge about the population level successful entrepreneurs. Maybe the successful age of good entrepreneurs is 24, let's say. So at the year of 24, typical successful entrepreneurs will become wealthy and pass down threshold or something like that, or achieve something of a milestone. Then you have a sample of potential entrepreneurs that may have the potential to be successful, and you want to test the age of this group. Is it similar to the knowledge that you have about typical successful entrepreneurs? You can test whether or not the average of this sample, their age, is equal to the number that you believe. So that is a one sample t statistic. Is comparing the sample statistic to the population property and to test equality. Here we are trying to compare, train, and test. So we are conducting a two sample t-test. We're trying to compare the same, the mean of the same variable x. It could be anything that is meaningful, that is potentially a key variable here. We want to make sure that the two sets have equal mean value for the x variable. That's when we use the t-test for equal quantity mean. We use t-test. Another test type is the test for equal proportion of the labels. This is suitable for categorical variables. Gender is one, and multi-label categories like marital status. It can be anything. Anything I can think of, job type, career, and family size, or family size may not be, maybe a numeric variable. So, so for gender, you can test whether the two sets have equal proportion of male and female. If gender variable is an important predictor variable, then you want to make sure that the proportion of males and females in both sets are similar. So that test, we use a z-test for that. So we'll take an example here and illustrate how to conduct the two tests. Test for equal mean is using t-test. We'll use one example here. This is one of the input variable in default 1 dataset. If you look at the data dictionary or documentation, paid is the amount of payment that is made in a particular month, and 5 means the 5th month, which is May, because the first month is January. So this variable is the amount of payment that each of the customer made in paying for the debt of the credit card balance in May. So this is clearly a numerical variable, and because it does have some correlation with the target, we want to make sure that the structural similarity is valid across the two sets, the train and test set, right? So we use a t-test. Now, the procedure of conducting hypothesis testing is consistent, is similar to what you are familiar with. We will first need to choose an alpha typically, but that is an implicit step that you don't have to, do very first. It's kind of in the background. The first real thing to define is what's a question behind your test, or what is the motivation for conducting this test. The motivation here is that we want to validate, we want to assess the structural similarity between the train and test sets in terms of the mean of paid 5. So the question is the average payment in May across the two samples of the customers the same in the two sets? So based on this, you have the null hypothesis. Null hypothesis is the status quo hypothesis. Is the hypothesis is the situation where most would agree that it will hold. And here, because the train and test set are splitted randomly, we would believe, or we would want to believe, that the average payment in May across the two sets are equal. So that's the equal mean hypothesis. That's a null hypothesis we want to actually support. But with every H null, we have HA, which is the alternative hypothesis. It's the opposite side of the null hypothesis. In all the previous examples that you experienced in other courses, it's mostly the case that you would like to reject the null hypothesis and accept the alternative hypothesis. That's those situations. You typically want to reject and accept, reject null and accept alternative hypothesis. Not the case here. We want to do the other side. We want to be able to accept the null and reject the alternative hypothesis, because we want to establish structural similarity. In this case, it's equal mean. If we end up rejecting the null hypothesis, we need to conduct the train test split one more time. So I hope that's understandable. And then follow the normal routine for hypothesis testing. You choose an alpha, which is typically small. It's a type 1 error you are comfortable with, typically 0.5, right? And then you conduct the test. You'll typically extract two statistics here, two quantity here. One is the t-stat and the p-value associated with the size of the t-stat. There are sometimes another quantity, which is the t-critical. You can look that up in the table, t distribution table. The purpose here is not to conduct scientific research. We're not trying to establish some scientific statement or scientific theory. We're trying to use hypothesis testing to verify structural similarity. So we're not going to make this very complex. By using Python and common tools, we typically only focus on the p-value. And the rule of making conclusions based on the test result, I think you're familiar, right? We compare the p-value with the alpha that we establish. If the p-value that we obtain from the test is so small that it's smaller than the alpha that we choose, the p-value is between 0 and 1. Alpha is also, but alpha is small. If the p-value we got is even smaller than alpha, we declare rejection of the null hypothesis, and we have to believe in the alternative hypothesis. For our case, it's mostly that p-value is greater than or equal, at least equal to alpha, and then we will fail to reject the null, which means that we accept the null, and we are good. We can proceed forward. Did these make sense? I think the procedure is familiar, right? So the homework asks you to do just that. Do several tests in that order and make a conclusion. And I have provided examples here in the slides. So let's do some demo here quickly. I think it's 7:43, but we only need 5 or so more minutes. Open the Jupyter notebook. So you only need one cell and 2 lines to conduct it. And one of these lines is to report the result. So to conduct the t-test, you need to first import the tool here. The tool is from the package stats models. Make sure that you install that. If you get an error saying no module found of stats models, that means you haven't installed the package. And follow the tutorial, the first tutorial about installing Python packages to install the module and the package. So once you import that, you can use the t-test individual sample t-tests, which is appropriate for our purposes. You will provide basically two columns to the function. It doesn't matter if you put the test set first and train set second. They just both have to be there. You have 2 arguments here. I'm comparing the paid 5 column, so I'm calling or indexing the column paid 5 of both of that train and test set, and which becomes 2 sample, and specifically about paid 5. And the test will compare sample mean and give you a few results, which is all in T results. And then I'm extracting the relevant results from that list. It's a tuple or it's a list. The first element with the index 0 of that return result will be the t-stat. The second element, which has the index 1, is the p-value. So let's run this, and I use the string format to print them and format them appropriately. Now, this means float. Both of these numbers will be floating point. They have decimals. I don't want too many decimal points. I'm limiting the number of decimal to be maximum 3. And I'm limiting also the width, the entire width of the whole number decimals to be 5. If there are if there are too many digits before the decimal, then the number of decimal points will be reduced to conform to the overall limit of the width. So let's run that. It's very quick, So the t statistic is 0.06. If you are familiar with the t stats, then typically t stats below 2 is typically not significant, and the p-value is it's over 0.5. It's much larger than 0.05. The alpha level is 0.05. Keep in mind. So our conclusion is that's the same result here. You can replicate them because of the random seed or random state. So you conducted the tests. The test statistic, the p-value is greater than 0.05. We conclude that we fail to reject the null hypothesis, and we accept the assumption that the mean of paid 5 variable across the train and test set is the same. So that completes the first test. Any questions? Good. Then the next example would be the testing for equal proportion of categorical variables. For example, gender. Binary variable will be a special case of categorical. You can have multi-class categorical variables such as marital status or income category, etc. And now we use target. Target is a binary variable here, so it's another example for use. So we'll compare we will try to compare equal proportion of those customers who churn inside each of the set, train and test, right? So the question here is the proportion the same, basically? Is the proportion of defaulted customers the same? The null hypothesis is that we assume they are the same because we believe by random splitting of the sample, they should be equal, but we are here to test. If you were asked to describe the alternative hypothesis, you would describe that the proportion of defaulted customers is not the same. You didn't have to specify which is larger. We don't care which one is larger. We just simply care that they are the same. So the alternative hypothesis would describe that the proportion is not the same. Then hypothesis testing, same procedure. Theoretically, it's same procedure. On implementation level, it's slightly different. You choose an alpha, which is similar, 0.05. You conduct the test, you get the statistic and p-value. This time it's z-test, so you get a z statistic. The distribution of z-stat and t-stat is slightly different, but quite similar. But the value, the meaning of the p-value is consistent. You compare the p-value with the alpha and proceed forward. So these are the same. Implementation are slightly different. So now to test proportions, you can't have a mean, right? You can't calculate the mean, but you have to get the statistics that are used to describe the proportion. So you need the count of one case in each set, and you also need the sample size for each set. So you will need 4 quantities to conduct the test. So that's why when you take a look at the proportion z-test function, even though it takes 2 arguments basically, but under each argument it's a list of 2. So you need 4 quantities to do that. On Jupyter Notebook, it's more clear what those are, right? So what you need is the count of those customers who defaulted in the train set, the count of customers who defaulted in the test set, and you also need the number of cases inside the train and the number of cases inside the test. So you put these into a list, becomes the first argument, and you put the other total sample size of the 2 sets in another list and provide it as a second argument. The ordering of these have to be consistent. You can do test first and train next, but you want to make sure that both are in the same direction, right? So I'm always going train first and test second because that's a convention. But to get these counts, it's trickier. I need to know the label. So I need to first print out some descriptive stats. I want to get the count, the label and the count of cases under each label of the 2 sets. So what I'm doing here is I'm printing the target column. I'm getting the target column and I'm using the value counts. As you remember, if you're taking the advanced programming, it's getting the frequency counts of each of the unique labels under that data set. So that column target with label 0 has count 551. Label 1, which is integer value. Label 1 has 149 counts within the train set. And the test set is smaller, so the number is smaller. So what I need is these 2 numbers, 149 and 51. So that's what these 2 lines of codes are doing. It's doing the same, generating the table, but it's extracting only the count for the label 1. And this is the label 1. So this value is 149. This value will become 51. And let's check. 149 and 51. So once I have these 2 values, I didn't have to prepare the other 2 because I can easily get them in the test level. So, I put these 2 values together in the list here quickly. And for number of observations of the train and test set, I'm getting the dimension and the number of rows, the first element of the 2 sets. And by the end, I have two arguments. I have two results, two output, basically. So I take them, I assign them directly into Z and P. And then I use the same print function as previously to report the results. So you will get the p-value as 0.121 and z as 1.5. Again, the p, although it's smaller, it's not yet as small as 0.05. So we will still accept the null hypothesis and conclude that the proportion of customers who churn is similar across the two sets. So that's it. That's the main content. A little bit over time, but any questions before I go forward? The next part it will be very fun. It's a counterfactual analysis of whether or not hypothesis testing really work. Any questions so far before I talk more about this? Any clarifications about hypothesis testing?
So what if we found that the mean or the proportion across these two sets are different?
Yeah, that's a very good question. If that's, let's see. Let's say you have 100 variables, right? And try and test that have 100 variables. Some of these variables are more important. Some of these are not as important because they have lower correlation with the target. But one critical variable is the target variable. You want to make sure at least if the target variable is a categorical variable, then you use the z-test to test every label of that target variable and try to establish equality, equal proportion between the two sets. If the result indicate that you should reject the null for the target, you definitely want to redo the trant-test split because the split is not successful. However, it's a different story for the x variable. That's why this question is very good. Suppose you have 100 input variable. The chance that you may reject the test for one of those 100 variables is quite high. That's by chance. For 100 variables, you can't be perfectly balancing everything. So for 100 tests of the input variable, if you get only a very low percentage of rejecting hypothesis, that's fine. But if you get an overwhelming proportion, let's say 25% of rejecting the equal mean hypothesis, then you probably want to reconsider the trant-test split. So that's, in a nutshell, that's how I suggest you do.
Thank you.
Great question. Anything else? Great. So let me talk about the fun part. You may wonder, we have done two tests and they are non-significant. It seems that we tend to get non-significant result and we tend to accept the null hypothesis. Does it always happen? What if we had a poor split? Will the hypothesis testing catch up? Or you bet they can catch up. So let's do an experiment here. This is what the rest of the demo does. Let's purposefully rank the data instead of randomly split. And let's see what happens. So I'm using, it's not that, this is conducting more t-test. You can do it yourself and try to understand the code. It uses a for loop and uses a different technique for the printing. If you have questions, let me know. So here, I'm using a different variable to sort. I'm not even using the paid 5, but because the payment amount has a correlation with the payment status. Payment status makes several qualitative different results. For instance, if a customer has paid in full, if a customer has only paid the minimum, if a customer didn't pay anything, it's a payment. It records the payment status, tiers of payment status, and it's reflected in the payment amount or by the payment amount. So those two variables have some correlation, and they are in the same month, so they have higher correlation. I'm using this variable to sort the data set in ascending order. The result of that is that the data set is not shuffled, definitely. The data set is sorted by a specific variable that is highly related to the variable that we want to test. So you can be sure that even if the target variable, not the target, but the variable that we want to conduct the test, which is paid 5, even though the data set is not sorted by paid 5, it's going to have some kind of pattern and split between those who paid little and those who paid a lot. You know, you can differentiate the good and bad customers in terms of using the credit card. And after sorting, it's a default sorted. I will take the top 70% of the data set and put it in the train. I would take the rest put it in the test. So you can imagine the train set have those customers whose payment status is either poor or good. And the test set is the other side of the story, other side of the coin. So the two groups will be most definitely likely to be different. By setting the number of cases to allocate to train and test, I'm slicing the rows of the two, I use iloc to slice using index value, the row index, to slice the first 700 cases to train, and the rest beginning 700 to 1,000, put them in tested in the test set. So I've done that, and you can take a look at the dimension here. It's the same as previously. The dimension is the same, or similar. Do I have more? I have more columns because
we removed we just took numeric earlier.
Yeah, I went from. I mean, I started from the fuller data set probably, but anyway. So the paid 5 column didn't change. Now let's conduct this test. This is exactly the same code as previously. Previously, it returned a non-significant result. Now we have a highly significant test result. The t-value is so big, the p is almost 0. If we conduct the equal proportion on the target labels, it will also return a highly significant test result. So that means the two sets are structurally very different, and you should consider redo the split, and you should examine how the split was done. Maybe the code was had errors leading to ineffective split. You want to investigate the codes and the operations. So that's it for today. And by now you should have everything that you need to complete the homework 1. Right? Homework 1 is about data, the basic operations of some theoretical questions that we talked about, as well as the data science basic warm-up exercises, some plots, and the last question is splitting the data set and conduct the hypothesis testing. I hope that after today's lecture and you can review the video, I hope you know what to do for the last question. If you have questions, let me know. Now let's open, I believe that's the end of it. Okay, let's open it for questions, for Q&A. Let me stop share for now. If you don't have any question about the slides, if you only have question about the homework, then I will stop sharing. So questions. If you don't have question, feel free to leave. Class is over, but we will use this time for questions.